Then when you're analyzing a magnetic circuit, you realize that this analysis is just similar to electric circuits. In other words, we just pick the analogy between electric circuits and magnetic circuits, and everything becomes simple and straightforward. So when you're talking about magnetism, we talk about magnetic materials, which are objects that produce a magnetic field. So if an object can produce a magnetic field, then it is also a magnetic object. And as you know, a magnet has a south and a north pole. This is very common. Almost everyone knows about that. And like poles repel, that is, if you put a north pole next to a north pole, they repel. Put a south pole next to a south pole, they attract. Unlike poles, that is the north, south, and the south pole, they attract. Okay, north pole and north pole repel, south pole and south pole repel. I hate if I say it, they attract. Then unlike poles are the ones which attract. So north and south, they attract. South to south, repulsion. North to north repulsion. Right. Then we also talk about a magnetic field. I think we talked about this when we were introducing capacitors. We're talking about electric fields. So in a magnetic field, we are still saying it is a region around a magnet where the magnetic field exists, or in which, if a magnetic material is put, it will experience a force due to the other magnetic body, then that becomes a magnetic field, and these are represented by magnetic flux lines, right? However, magnetic flux lines are different from electric flux lines in that they don't have an origin or a termination point. So you realize that for electric flux lines, we say they move positive to negative, right? And usually electric flux lines, we don't expect them to go so much into space. But for magnetic flux lines, they are actually radiated from the North Pole to the South Pole and return to the North Pole through a magnetic bar, which means that magnetic flux lines actually create or make a closed loop, right? They make a closed loop. Now, those are magnetic flux lines, right? So we have different orientations or presentations of magnetic flux lines due to different sources of magnetism. So the magnetic flux lines due to a permanent magnet, that means one which is a permanent north and the south pole, they try to occupy the smallest possible area, right? And the strength of the field at any given point is determined by the density of the flux lines. Just the same as the electric flux lines, the strength at a point is determined by the density of the flux lines. The denser the flux lines, the stronger the field, right? Then, if you put unlike poles of grounded magnets together, they will attract, and that is the flux distribution, which is observed as given in that diagram. That is our flux distribution. So you realize that they have north to south in between the two. Then outside, they go around in a loop like that, creating closed loops in their paths. That's how our magnetic field radiated. If you put unlike poles, then the magnetic field flux lines, if they come towards each other, they will repel each other, right? Then if they are in the same direction, they even enforce more repulsion. So you see that they create almost like a neutral zone between the magnets, right? In this case, we have south to south. The lines are radiated into the magnet, and we have a neutral point where we're saying there is no net magnetism there, right? Then if you place a non-magnetic material in the path of the flux lines, they are not affected. So this is what happens. They just pass through as if they are passing through for a non-magnetic material. But for a magnetic material, right, the flux lines tends to be concentrated in the magnetic material, right? Because it is a low reluctance area, that means it offers minimum opposition to the establishment of flux within it. Therefore, flux line tends to diverge and get into the magnetic material. When they get out, then they separate as they will. So a glass will not affect the distribution of a magnetic field, but a magnetic material will affect the distribution of the magnetic field. Then, if a magnetic material such as soft iron is placed in flux paths, the flux lines will pass through the soft iron rather than surrounding it, because the flux line pass with greater ease through magnetic materials than through air. That is what I was explaining. And that principle is used in what is called magnetic shielding. So when I say we are shielding a material, let's say for measurement instruments which use magnetism, for them not to be affected by stray magnetic fields, you put a magnetic material around them so that when the stray magnetic field radiates its flux there, instead of the flux passing through the instrument and disturbing it, it will pass through that. So you realize that if it's a canvas, then it will be shielded like that. Then the arrow shows north pole and the like will be, south and north and east and west, whatever. It will not be affected, because when the fluid gets in there, it's trapped in the magnetic material. That is the concept of magnetic shielding that I'm talking about, right? Then there's something which is called a solenoid, which is a form of an electromagnet, which is used to generate a controlled magnetic field. So when you talk about a solenoid, we are saying you have a magnetic material and you wound a wire around it. Then you induce you push a current through the wire. Then it will produce a magnetic field. Let's say it gives a south and a north. So it becomes a magnet, but then it's an induced magnetism, which means when the current stops flowing, the magnetism disappears. So in that case, it becomes a solenoid, right? If it is used to produce a controlled magnetic field, or becomes an electromagnet, right? So these are some of the components that are used, let's say, in magnetic doors and the like, whereby if you energize, let's say the solenoid is this side, right? Okay, so it should be wound this way, right? Then it gives a north pole and the south pole there. Then on the other side, maybe a permanent magnet with a south and a north pole. So when you energize, then the two magnets will attract each other and they lock the door. When you de-energize, the magnetism disappears and the door is unlocked. So that is where it might be used. So a long circle of wire can be used nearly uniform magnetic field similar to that of a permagnet. The direction of the flux lines can be found using the right-hand rule. So if you hold the solenoid with the right hand, say that the fingers curl in the direction of the current. So this will be your fingers. So they should be curling in the direction of the current. Then the thumb will point in the direction of the north pole, right? Now, when we talk about magnetic flux lines, we say they are radiated from the north to south. So in other words, the thumb will also be pointing in the direction of the flux. That's the right-hand rule which you can use to determine the direction of the magnetism. Meaning to say, if you reverse the direction of the current, then this will become the north and that becomes the south. That is the concept of the right-hand rule that I'm talking about. Then we also have magnetic field due to a current carrying conductor. So if a conductor is just carrying current, it has an associated magnetic field, right? Again, we use the right-hand grip rule or the right-hand screw rule, right? So what do? You just grip the conductor such that the thumb points in the direction of the current through the conductor. So in this case, the current will be moving up. Then the fingers will curl around the conductor in the direction of the field, right? They will curl around the conductor in the direction of the field, right? That is the right-hand grip rule. So the right-hand rule is used for a solenoid and also for a current carrying conductor. So again, for the right-hand screw rule, if you want, let's say you know the direction of the current, if your current is moving downwards, then you just determine the direction in which you should turn the screw so that it goes down. That will be the direction of the field, and the direction of movement of the screw becomes the direction of the current. Right. Now, in current carrying conductors, we usually represent them in these two forms: the dot showing the tip of the arrow, meaning to say the current is coming into and out of the paper that way. Then this would be the tail of the arrow, meaning to say the current is getting through the top, coming out through the bottom of the paper. So this is like a planner. So if you put a dot and a circle, we know that current is coming upwards. Then that means it's the direction of the thumb. Then the fingers will go in that direction. Current is going down, your thumb is going down, your fingers will go in that direction. You can just test it with these conventional methods. So when the current is going into the paper, then you see the tail, which is the X. When it's coming out of the paper, that is towards you, you see the head of the arrow. And then you determine the directions in that simple way. So those are the fields and characteristics of our magnetic fields. Then the next thing, we also want to get the characteristics of the magnetic field, in as much as we also deal with the characteristics of the electric field. So in magnetic fields, we still have flux and flux density, though we put magnetic field flux and then magnetic flux density, right? So for flux, it is measured in Webers, Wg represented by phi, that's flux. The number of flux lines per unit area, that the flux density here is represented by B measured in Teslas T, right? So magnetic flux density B becomes equal to flux per unit area. B is equal to phi over A. That becomes our magnetic flux density. B is equal to phi over A. Okay? Phi in Webers, A in square meters, and B in Teslas. Then there's what is called the MMF, or magnetomotive force. Remember, we talked about EMF in electric fields. We'll say is the force which causes the charge to move. In a magnetic field, magnetomotive force is the external force required to establish flux in a material. So the force required to establish flux in a material is the MMF, magnetomotive force. Symbol is the F. So it's not the normal F, it's something like that. F is called Ni, meaning to say, if you have a certain number of coils wound around a material, let's say N, and the current flowing through it is I, then the MMF becomes the product of the number of turns times the current, measured in ampere turns. Some books will write just as ampere, since turns do not have a unit. But for us, let's say they're measured in ampere turns. Magnetomotive force defined as the MMF per unit length of magnetic path. Symbol H, that's the magnetizing force. So H is equal to magnetomotive force over the length of the magnetic path. So realize that in magnetic field, we talk about the path. Right? The difference is that in electric circuits, you are given resistance and the like. Here we talk about the length of the path, which determines its, in loose terms, let's say its resistance to the flow of flux. So once this is a current I, and we have N there, using our right-hand rule, you realize that the flux will be radiated in this direction through this is the magnetic material, right? Then the flux will be going that direction, and the length will be, let's say, from here to back. That becomes the length of the magnetic path. Remember, you could use length to measure resistance. R is called rho A over A. Here, you can also use length to calculate the opposition to the establishment of flux by a second. Then we go on to permeability. Remember, in electric circuits, we talked about permittivity. In magnetic circuits, we talk about permeability, right? So, you realize that if you use different cores for your solenoid, for example, and then you use the same current and the same number of turns, you realize that the strength of the magnetic field becomes different. Why? Because the materials have different permeabilities, right? So if a material has high permeability, that means it easily allows the establishment of flux through it. If it has low permeability, it has some resistance to the establishment of the flux. So permeability given by mu, that stylish U there, mu, is a measure of the ease with which magnetic flux lines can be established in a material. So we're talking about how easy is it to establish flux lines in a material. That becomes its permeability. Okay, how easy it is to establish that becomes the permeability of the material. right? So permeability of a vacuum or a free air is given by 4 pi and 10 to the power of -7. That is the permeability of free space or of a vacuum, right? 4 pi and 10 to the power of -7, and we call it mu naught, right? So this is roughly taken to be equal to the permeability of air, and it's measured in Webers per ampere meter, right? So we have two types of materials. If a material has a permeability slightly less than that of free space, that is slightly less than this value, it is called a diamagnetic material. And those with permeability slightly above that of a free space or a vacuum are called paramagnetic materials. Then we have materials such as iron and nickel, steel, and other alloys, which have very high permeabilities of the order of hundreds or thousands times that of a free space. They are now referred as ferromagnetic. So you hear people talking about ferrous material and the like. Usually when they talk about ferro, they're talking about iron. So those materials are ferromagnetic. Those are very highly magnetic material. Then the relative permeability, which is also analogous to our relative permittivity, becomes equal to the absolute permeability of a material divided by the permeability of a vacuum or the permeability of free space, which is mu naught. So mu r is called mu over mu naught. In other words, mu is called mu r times mu naught. So based on permeabilities, that is what I was explaining, diamagnetic material, paramagnetic materials, and ferromagnetic materials. Paramagnetic lower than vacuum, slightly higher than the vacuum, slightly. Diamagnetic slightly lower than that of the vacuum. Ferromagnetic several hundreds or thousands times higher than that of a vacuum. Now, when we're talking about magnetic circuits now, we are saying we still have the path which allows flux to flow, and that path is our magnetic path, and the source will be the MMF generated by the current and the number of turns, right? And so on. So as a result, you realize that in this case, the flux will go in that direction using your right-hand rule, right? Then, this material in which the flux flows also is some opposition to the flow or establishment of flux. And that opposition is what we call reluctance. Okay? So, for electric circuits, the opposition is the resistance. For magnetic circuits, the opposition is the reluctance. And the cause in electric circuits is the EMF. The cause in magnetic circuits is the MMF. And the effect in electric circuits is the flow of current. In magnetic circuits, it is the establishment of flux. So, in as much as we said R is got rho L over A, right? If you look at it closely, reluctance is now L over mu A, right? Then, if you look closely at the equation, you realize that resistance is proportional to opposition or the difficulty. Reluctance is inversely proportional to the enablement or the permeability, which is how it allows. So L over A, it's similar in both cases, rho L over A. But in resistance, we are multiplying by resistivity. In reluctance, we are dividing by permeability. So L will be the length of the magnetic material of the magnetic circuit. A is the cross-sectional area, that is this area, if we were to measure it, this cross-sectional area through which the flux is being established. Then mu becomes the permeability of that material, which makes up the magnetic circuit, and the unit becomes ampere turns per Weber, which is mmf over phi, as we saw. So the flux density and magnetizing force are related by the equation B is got mu H, right? So the magnetizing force H divided by B is equal to mu over H. Hence, we can still apply Ohm's law to magnetic circuits. So this is analogous to your current, then analogous to the voltage, and this analogous to your resistance. So you can see that it's still Ohm's law, but here it's Ohm's law for magnetic circuits. It's Ohm's law for magnetic circuits. So if you rewrite it, you realize that flux is equal to mmf over reluctance. All right. Then one thing that you have to take note of is in magnetic circuits now, we calculate reluctance. In electric circuit, we give you the resistance 10 ohms, 15 ohms, and the like, and you just go and punch in the values and proceed. But in our magnetic circuits, we have to calculate the reluctance based on the length, the type of material, and the cross-sectional area, right? So that is the difference. That is the difference between an electric circuit and a magnetic circuit. So realize that the calculations in our circuits are a bit slightly difficult because of that. Otherwise, all the methods that we use in circuit analysis, they are still applicable in our analysis, right? So we can still do the series, parallel circuits, and the like, but after calculating reluctance. So you realize that that is where the difference comes in. So as an example, this is an example, right? Okay, let's go back a bit. So also we have laws for magnetic circuits, just as we have laws for electric circuits. So the sum of mmf rises is equal to the sum of mmf drops, right? I'm sure I still remember what this is. This is Kirchhoff's voltage law, right? So here it is Ampere's second law, right? In other words, in this case, the sources it's Ni, then the drops are HL, then their sum should be equal to their sum, analogous to that. In other words, in this circuit, we have iron, which is its own length, we have steel, which is its own length, copper, which is its own length. In other words, we have three reluctances, right? And one mmf. So we could represent it by an equivalent magnetic circuit where this is Ni, right? Then this is our reluctance for iron, all right? Then the next one will be for R steel. Then the next one will be R cobalt. So the representation of the physical magnetic circuit is this, but this is also an equivalent circuit. So if you calculate R iron and calculate R steel and R cobalt, then the total reluctance is still the same as series resistances. And then the drops across this should be equal to the MMF produced here. This is what we are talking about just here. Right? So magnetizing force of AB times the length of AB, magnetizing force of that times the length of that, it still comes back to the same circuits. Right? Then also we have junctions in magnetic circuits, and still flux entering a junction should be equal to flux leaving a junction. In other words, that's why phi A is called phi B plus phi C. Right? Why? Because A is entering this junction and these two are leaving. That's this and that. So again, the same laws apply. All you have to do is be able to calculate the fluxes, then use your current divider rule for electric circuits to also divide between the fluxes. Right. For example, determine the current I required to establish a flux of 1.5 and then above minus 4 wafers in the section of the core indicated mu R is called 640 for steel. Right. So this will be your solution. And I'm sure this example is in Boystad. You can look for it in Boystad, I'm sure you will find it there. Right? So what we are saying is, if this is the same material, so from here to there, this can be one reluctance. From here to there, that's another reluctance. Then you have a center reluctance. So in other words, our equivalent circuit will be MMF there, reluctance 1 in the outer, reluctance 2 in this other section. Then we have another reluctance in the center leg. Right? So you can calculate this reluctance and that reluctance from the dimensions given there. Then after that, MMF over total reluctance will give you the flux, just like the current. Then you do the division, just like your current divider rule, to get the different values there. So can you snapshot that quickly as we move? Can you snapshot that? But I'm sure this example is in Boystad. If I'm not mistaken, I think I took it from there. You can just check. So that snapshot that. Try to calculate using R is called L over mu A. And let's see what you get from there. Okay, I hope you snapshot that. So that is our equivalent circuit, which I was drawing. Reluctance, that reluctance, and the other reluctance. Then we go on to inductance. So for today, we end here. Tomorrow we start on inductance and inductive transients. So let's just go back, revise, and try to read what we have covered on magnetism and magnetic circuits. Okay. So I'll stop recording. And once that is done, you can find the video.